Good morning, dear students. A warm welcome to all of you for our today's digital session for the subject Science and Technology Section A. In our previous session, we have started with a new chapter from Physics, chapter number 4, Effects of Electric Current. Last time, we have studied how energy transfer takes place in an electric circuit, and then we had derived Joule's law of heating. Also, we had studied about the heating effect of electric current, and our topics for today are magnetic effect of electric current and Fleming's left-hand rule. Before we move to our today's topics, as usual in the beginning, for the first 5 minutes, we are going to revise what we have studied in our previous session, and then we will proceed to our today's part. So let us see what are the different applications of heating effect of electric current and what it actually means. I had told you. Now, whenever electrons they move in a metallic conductor in a wire, they collide with each other. They are in a state of random motion. When the energy is supplied to the wire, they start moving from one end to the other, and in being in a state of random motion, they collide with each other. Not only that, they collide with the atoms and ions of that metallic wire, and at every part of collision, some amount of energy, which energy? Kinetic energy. How it is possessed by electrons? Due to the movement, that gets converted into heat, and slowly the temperature of the conductor, the wire, increases, and that is known as heating effect of electric current. Heating effect means what? Because of the flow of electric current, the heat is generated, and on this heat, different electrical appliances work. We had seen last time cooker, toaster, or the geysers, electric bulb. These are the different applications of heating effect of electric current. We have studied about an electric bulb in details last time, and I have told you in an electric bulb, the filament of the wire is usually made up of tungsten. Why tungsten? Because this tungsten metal, it has a capacity of getting heated to about 3400 degrees Celsius, and you know the appliances or the different applications of heating effect, they need more amount of heating. So if the wires are made up of metals using low melting point, then it is likely that when more amount of current will flow, the wire will melt and your bulb will stop glowing. Then a harmful effect of electric, you can say heating effect, we have seen is short circuit. I have displayed here a figure, a diagram, or you can say an image of short circuit being caused in a building. What is short circuit? I have told you last time, the home electrical connection. It consists of live, neutral and earth wires. Out of these two, when the fault in the equipment is seen or the plastic coating on the live and the neutral wire gives away, these two wires, they come in contact with each other, and a large amount of current is seen flowing through it, producing more amount of heat. Or I had also told you last time, during short circuit, what happens? The resistance of the circuit becomes very small and huge amount of current starts flowing, producing a large amount of heat and raising the temperature, and as a result the circuit can catch fire, and this entire process is known as short circuit. If any inflammable material such as wood, plastic, cloth exists around that place, then immediately it can catch fire, and in few seconds, in no time, your all appliances or your house, your buildings can be set into fire. So it has to be taken care to see that the plastic coating on the live and neutral wires are always in a proper way. The insulation of the wires should be checked periodically. Next is overloading of the circuit. Now here also I had told you, during short circuit, if you want to save your appliances from getting damaged, then it is only the fuse which is used as a precautionary measure. Then we have studied about overloading of the circuit. Here I had told you, when high power rating electrical appliances such as air conditioners, geysers, electric ovens and all, they consume high amount of electricity, hence they are called as high power rating electrical appliances. So if they are switched on simultaneously, then it can lead to overloading of the circuit. Why overloading? Because more and more amount of current is to be drawn from the transformer beyond its capacity, and this is known as overloading. And the only way to protect or get saved from overloading is that you should not connect many appliances, especially of high power rating, at the same time in the circuit. Then we have moved to the next topic, which is our today's topic, magnetic effect of electric current. I have told you that this effect was accidentally discovered by the scientist Hans Christian Ørsted. You can see his photograph over here. He was working with some electrical appliances, and what happened at that time? He was doing some experiments with some electrical equipments, and he saw that when he passed strong electric current through the wire, a nearby compass needle got deflected, and from this he inferred that it was the electric current which was flowing through this wire which was producing magnetism, and this concept he gave the name as electromagnetism. Why electromagnetism? Because of the flow of electricity, magnetism is produced. So magnetic effect is observed because of the current in the wire, and Ørsted pointed out the relationship between electricity and magnetism from this accidental invention or discovery. After that, we are going to move towards our next topic for today, the right hand thumb rule. In this chapter, you have to study 3 rules. One is the right hand thumb rule, one is the Fleming's left hand rule, and one is the Fleming's right hand rule. So 3 rules you have to study, you have to learn it by heart. Here, right hand thumb rule, in the beginning only you can see imagine word is there. Imagine that you have held the conductor in your right hand in such a way that your thumb points in the direction of the current. You can see this. Why they have told the word imagine? Because you have held the conductor, and conductor means the substance which allows the flow of current. So if you are holding something through which current is flowing, that is not right. So they have used the word imagine. Imagine that you have held the conductor in your right hand. So right hand thumb rule. If right hand word is not there in the exam, half mark will be deducted. How you are going to hold? In such a way that this thumb is pointing in the direction of electric current. Turn your fingers, curl your fingers around the conductor. Then the direction of the fingers is the direction of the magnetic field or the magnetic lines of force. This is the right hand thumb rule which you have to study it by heart. Now whatever may be the rule, left hand rule, Fleming's right hand rule, right hand thumb rule, if you want to make your paper more qualitative, you have to support your rule with the help of a diagram. Now here while drawing the diagram, the hands and all artistical, or you can say artistic way, you don't want it to draw it in a very, you can say we are not attending our intermediate exams and all. So you can just show the fingers, the thumb properly, and the flow of current, the which fingers are showing the magnetic field. That much is enough. When you are writing the rule, whether it is the left hand, whether it is the right hand, mentioning the hand, right hand, left hand is very important. Now we move towards our next topic, magnetic field which is produced by current through a circular loop. Now you all know what is a circular loop. You can see here a loop. How is a loop prepared? How is a circular loop prepared? It is made by just bending your conductor. So in the case of the current which is passing through a circular loop of a conducting wire, that is the wire which is conducting current, the magnetic lines of force is the field which is produced by a current flowing through a loop which is made by bending of your straight wire. You can clearly see here in the diagram. In this figure, what you can observe is a circuit is completed by connecting various components. You can see the ammeter, you can see the battery over here. You can see here carefully in the figure how the various components are joined and the circuit is completed. So when the circuit is completed and if the current passes through the loop, the magnetic lines of force are produced at each point of the loop. You can see this. At each point of the loop, you can see the magnetic lines of force being produced. And as we go away from the wire, as you move away and away from the wire, this concentric circles, the circles are representing what? They are representing your magnetic lines of force. As you go away from the wire, they will become bigger and bigger. And as you go towards the center of the loop of the circle, they become so big that its arc, it can be shown as a straight line. Now here you can see in this figure, the magnetic lines of force, they are shown near the points P and point Q only. However, they will be created near each point on the loop. Here in the diagram you can see that they are created at only point P and Q, but in practical way you can see that this magnetic lines of force, they will be created near each point on the loop. And by making use of the right hand thumb rule which we have studied just now, you have to check that every point on the loop, it contributes the magnetic lines of force at the center of the loop, and this lines of force at the center of the loop, they are in the same direction. So what will be derived over here? What it will result in? That the magnetic field which is produced by a current carrying wire at a given point, it depends directly on the current passing through it. It is dependent on the current. And here, if a coil has n number of turns, the field, the magnetic field which is produced is n times larger than that produced by a single turn. And why this is possible? This is possible because the current in each circular turn, it has the same direction. That is why I have told you, you have to check by making use of the right hand thumb rule that every point on the loop, it contributes the magnetic lines of force at the center, and this lines of force at the center, they are in the same direction, and the field due to each turn then just adds up. If you want to add the number of students standing in a row, all should be in a single row, one behind the other. If any of the child just moves from the path, then the addition of that child won't be done. Similarly here, you have to ensure that the direction is same. Next we move towards magnetic field due to a current in a solenoid. Before moving towards this topic, we have to first understand what we mean by the term solenoid. What is a solenoid? A very simple definition of solenoid is a coil of many turns of insulated copper wire. You can see here turns of copper wire which is wrapped in the shape of a cylinder. You can see here a cylindrical shape, that is known as a solenoid. or in physical terms, when a copper wire with a resistive coating is wound in a chain of loops like a spring, it is called a solenoid. It can be asked as a, you can say definition or true and false. So you have to be prepared with the definition of solenoid. Now here you can see the magnetic field lines in a solenoid through which, now through this solenoid current is passing. These lines are similar to that of the lines of a bar magnet. You all know what is bar magnet. One end of the pole, one end it acts as the north-south pole and the other end it acts as the north pole, and hence the solenoid has all the properties of the magnetic field which is produced by a bar magnet. Here the one end I have told you it acts as the magnetic north pole, other acts as the south pole, and hence the magnetic lines of force inside the solenoid, if you can see carefully, they are parallel to each other. And what does this mean? The intensity of magnetic field within the solenoid is uniform. It is same everywhere. So the magnetic field in a solenoid is uniform. It is same. Now for your information, this is not given in the textbook. I will tell you. With the help of this solenoid, you can even magnetize a piece of rod of a given material. And if the rod is hard steel and if the magnetic field is strong enough, even permanent magnets can be produced. Now permanent magnets, you know, it has n number of uses. They are used in microphones, loudspeakers, electric clocks, ammeters, voltmeters. So magnetic field due to current in a solenoid, if the field is strong enough and if the rod is hard steel, then permanent magnets can be prepared from it. Now I know these topics are slightly difficult for you to grasp because it is anyhow physics, and most of the topics in physics are imaginary. So you have to read the topics n number of times to understand the concept. Do not learn it. Our next concept is force acting on a current carrying conductor, current carrying wire which is placed in a magnetic field. You can see this experimental setup wherein you have a flexible copper wire. You can see this dotted lines if you see carefully. Electric cell, a horseshoe magnet with strong magnetic field, a horseshoe magnet with a strong magnetic field. Now using the stand, you can see the stand on the left hand side, fix the copper wire so that it passes through the poles of the horseshoe magnet. You can see here in this figure. Now here two you can say conditions are there. One is when a current is not flowing through the wire, then it remains straight at position A. You can see this position in the middle, position A. This is the position of the wire when the current is not flowing through it, and when the current flows from top to bottom, the wire bends and it comes to position C. You can see this position C on the right hand side. Now if the current direction is reversed, reverse means it is allowed to flow from bottom to top end, then the wire bends but comes at the other position, that is position B. What does this mean? What does this indicate? It indicates that the direction of the force on the wire is perpendicular to both the magnetic field as well as the direction of the current. And here the direction of magnetic field, it is from north to south. You can see here current from bottom to the top. And what here you notice in this experiment is whenever current flows through a wire, whenever current flows through a conductor, in the presence of magnetic field, a force is exerted on the conductor. And if the direction of the current is reversed, the direction of the force will also get reversed. If the magnet is kept in a reversed position, that is its south pole is brought at the position of its north pole. This is the south pole. If it is brought at this position, at the position of north pole, and north pole is brought at the position of south pole, what can you infer, what can you observe? Here you can observe that when the magnetic field position is reversed, then the direction of magnetic field, the current flowing through the conductor, it will also get reversed. Now, as I have told you, a force is exerted on the current carrying conductor. This direction of the force, it depends on both. Both means what? It depends on the direction of the current and the direction of the magnetic field. Now, what type of questions are likely to be asked on this part of the chapter? You have studied about the magnetic field due to current in a circular loop, current in a solenoid. Here direct questions will be asked, or this experimental setup and all will be given to you. They can ask you the different questions based on this experiment. That what happens when the current flows through the wire, what happens when the current is not flowing through the conductor, what happens if the current direction is reversed, that is from bottom to the top, and then what does the direction of the force which is exerted on the current carrying conductor, it depends upon. So just understand the concept, do not learn it. Today we have studied right hand thumb rule. Our next rule which we are going to study is Fleming's left hand rule. And as I have told you earlier also, if you want to make your answer more impressive, then support your rule with the diagram. Now, if you want to show this diagram, you are welcome, or you can show this indicative diagram also, any one of them. What does this rule tell you? According to this rule, the left hand thumb, the index finger and the middle finger are stretched so that they are perpendicular to each other. You can see making an angle of 90 degree. Now stretch in such a way that the thumb, index finger and the middle finger, they are perpendicular to each other. Now here if your index finger is in the direction of magnetic field and the middle finger points in the direction of current, then the direction of the thumb is the direction of the force which is exerted on the conductor, on the wire. This is Fleming's left hand rule. Ahead also you have one more rule, Fleming's right hand rule. Here please do not forget to mention the left hand. What does this rule state? Once again I will tell you, stretch the thumb, the index finger and the middle finger of your left hand mutually perpendicular to each other. If the index finger shows the direction of magnetic field and the middle finger shows the direction of current, then the thumb is the direction of the force exerted on the conductor. After that, if you see in your textbook, you have the topic of electric motor. Electric motor and electric generator. I want to take these topics together, which will not get over in today's session. So in tomorrow's session, I will take both these topics together, that is electric motor and electric generator. Before completing our today's session, a small topic you have to understand, electromagnetic induction. What do you understand by this term, electromagnetic induction? In short, I will tell you. In short, production of electricity from magnetism is called electromagnetic induction. Induction, inducing something. Production of electricity, generation of electricity from magnetism is called electromagnetic induction. We can produce current by moving the conducting wire inside a fixed magnetic force or magnetic, you can say, field. And if we keep a conducting wire near the magnetic field of a magnet and just move on vigorously, current will be induced in the wire. Current will be induced in it. Now we will understand in physics what does this electromagnetic induction mean and who had first studied about this concept. The main theme here of the concept is when a current carrying conductor is placed in a magnetic field such that the direction of the current is perpendicular to the magnetic field, it experiences a force. But if a conductor is moving inside a magnetic field, you can say, or magnetic field is changing around a fixed conductor, electric current is produced, electric current is generated. This is known as electromagnetic induction, and it was first studied by Michael Faraday. In short, what you can say about electromagnetic induction, or how you can define it: the process by which a changing magnetic field in a conductor induces a current in another conductor. It is called electromagnetic induction. You can see an ammeter is placed over here. You can see where is the position of the magnet. No current is observed. Whereas when you see the magnet is moved towards this coil, then the current flow can be immediately noticed from the movement of the pointer of ammeter. So here, in short, you can say the process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. This topic you are going to apply in electric generator. Next, we are just going to get ourselves introduced with electric motor and generator, and in details we are going to see in our next session. Electric motor, EM. Just remember, a device which converts electrical energy into mechanical energy is known as electric motor. Why I told you EM? Because here it is exactly vice versa. Electric generator, a device which converts mechanical energy into electrical energy. You can see here EM, if you remember, electrical into mechanical. So device converting electrical energy into mechanical energy. Its setup, its construction, how it works, whether a battery is required, all that we are going to study in our next session. For generator, you can see in place of battery, you can see a galvanometer. What are its setups, how the rings and all they work, we are going to see later on. And hence I request all of you, when you attend the next session tomorrow, go through both the topics of motor and generator. With this, we end with our today's session. Let us meet online tomorrow, and I hope you are going to read and go through the topics thoroughly. Thank you, dear children.